Hello, everyone, and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now we're just going to get started on our set of questions for today's session. Okay, so question 1 asks, a disproportionation reaction involves a substance that acts as both an oxidizing and a reducing agent, producing a higher and lower oxidation states of the same element in the products. Which of the following disproportionation reactions are spontaneous under standard conditions? Calculate delta G and K at 25 degrees Celsius for those reactions that are spontaneous under standard conditions. So they have A and B, which I think are just examples of disproportionation reactions, and we are going to be looking at C. So I'm just going to write the unbalanced reaction down, and then I'll also show all the steps on how we would balance this. So we start off with chlorous acid, and then this forms chlorate, which is ClO3 minus, plus hypochlorous acid. So this is HClO aqueous. Okay, so this is our unbalanced reaction. So the first step in balancing redox reactions is to write the two half reactions. So the reduction reaction and the oxidation reaction. So we're just going to break this unbalanced reaction into two. So the first one, I'll write the oxidation reaction. Then this is H. So the chlorous acid making chlorate is the oxidation reaction. And then for the reduction, it is the chlorous acid making the hypochlorous acid. Okay, so step 2 is to balance all the atoms. So typically you want to balance all the hydrogens and the oxygens. And you also want to balance the charges. So I'll show how we would do that. Okay, so just rewriting oxidation and reduction. Okay, so let's look at the oxidation reaction first. You'll notice that there is a hydrogen on one hydrogen on the reactant side, two oxygens on the reactant side, and then three oxygens on the product side. So first, I'm just going to write like a box over here. We are going to add water to add oxygens. And then assuming this takes place in acidic conditions, we are going to add protons to add hydrogens. So we want to add the water first, since it contains hydrogens, and it'll just be easier to balance out if we add out the water first. Okay, so again, we need an oxygen on our reactant side. So I'm going to add water. So now the oxygens are balanced out, but our reactants has 2 hydrogens, or 3 hydrogens, sorry, and our products has none. So now we can add H plus to balance the hydrogens out. So we need 3 H plus ions. And now we want to make sure that the charges are balanced as well. So on our reactant side, all the charges are neutral. There are no charges. And for the products, we have a single negative charge and we have 3 positive charges. So therefore, to neutralize the positive charges, we need to add 2 electrons. Okay, so let's do something similar to our reduction reaction. We start off with the chlorous acid, and you'll notice that for this, there's 1 extra oxygen in our reactant side. So I'm going to add water to my product side. So now there are 3 hydrogens on my products. So I need to add 2 protons to my reactants. And then to balance out this positive charge, I need to add 2 electrons as well. Okay, so now everything should be balanced in terms of atoms and in terms of charges. So the third step is just to combine both of the half reactions. So when we combine the half reactions, we want to then also cancel out anything that is the same on both sides. So I'm just going to combine them. So we have water, and we also have 2 moles of chlorous acid in total, 2 protons and 2 electrons. And then for our product side, we have the chlorate ion plus 3 protons plus 2 electrons plus hypochlorous acid plus water. Okay, so I'm going to cancel out the water since it's just the same on both sides. There are 2 protons on the left and 3 on the right. So I'm going to cancel this whole thing, and we're left with 1 proton on the right. The electrons cancel out as well. And then our final balanced, net balanced equation is the following. Yep, so now we have our net balanced reaction. So step 4 is to find the overall reduction potential. So this can be expressed as E cell is equal to E cathode plus E anode. So this is given in the question. So for the cathode, it is 1.21. So that is our reduction reaction. And then for the anode, it is going to be negative 1.65. Oh wait, actually it's the other way around. So in the cathode, it's 1.65. And then the anode is negative 1.21. And then this is in volts. And then we have an E cell of 0.44 volts. So this means it is a spontaneous reaction. So I'm just going to start a new page because this is a long question. But basically step 6 is to now calculate for delta G. So delta G is equal to negative N times F, and then the potential, which we calculated in the previous step. So N is the number of electrons transferred. So if we look at our net balanced equation, there were 2 electrons that were transferred. F is Faraday's constant, and its value is 96,485.33 coulombs per mole. And then our potential is 0.44 volts. Okay, so multiplying this out, we end up getting negative 84,907 joules. So the reason why we have joules as our units now is because joules is equal to volts times coulombs. So now we can just express it as joules, and then this is per mole. Okay, so now step 7 is to find K. So we can find K using the equation delta G is equal to RT ln K. So now let's rearrange this equation to solve for K. So it's going to be ln K is equal to negative delta G over RT. So R is just a constant. I'll write it out below, but the delta G is just what we solved in the previous step, negative 84,907 joules per mole. And for our R, it is 8.314 joules over moles times Kelvin. So this is usually given in the question. And the temperature is 25 degrees Celsius, but we want it in Kelvin. So it is 298 Kelvin. Okay, so this whole value here is equal to 34.27. So now, and I'll just rewrite it here. So ln k is equal to 34.27. And then in order to isolate to solve for our k, we need to get rid of the ln. And to do that, we use, we base the e on both sides. So if you have a scientific calculator, you can just plug that in. And then you should get a k value of 7.6 times 10 to the 14. Okay, so long answer. But let's see what our junior tutor said. I'll start from page 1. So they wrote out, they showed that the anode, the chlorous acid is oxidized to chlorate, and at the cathode, the chlorous acid is reduced to hypochlorous acid. Balancing the charges to balance the charges, adding electrons to the more positive side or electron deficient side, and to make the equal, multiplying both the equations by the lowest common factor among both the reactions. Yep, so I guess they already... Oh, it's because the half reactions were given already, right? Yep, so they just did the same thing. So they added both half reactions and got a net balanced reaction. The same as mine. We can find the reduction potential for the overall reaction by the equation E cell is equal to E cathode plus E anode. And they got 0.44 volts. As the value is positive, the above reaction is spontaneous. Then they found delta G. So I did that on this page. 2 times Faraday's constant times the potential of the cell, and they got negative 84,907 joules per mole. And then finding K by using the given relation, delta G equals RT times ln K. Okay, so they converted ln to the log, but either way works. Where R is 8.314 joules per mole Kelvin. T is 298. And they ended up getting 7.584 times 10 to the 14. Yep, so this solution is correct. Okay, moving on to question 2. What is the major organic product of the reaction shown below? So we have an alkyl halide reacting with water and isopropyl alcohol. Okay, so 2 different reactions can take place. You can have an SN1 product. So this is through a substitution reaction. And through hydride shifts, another product that could be formed is if the alcohol was with the tertiary carbon instead, since this is more stable. So I believe this will be our major product. And I'll write down the mechanism for both of these below. But the second product that you could get is through elimination. And basically this is when a double bond is formed. Okay, so I'll just note this is the substitution. And then this one was through elimination. Okay, so I'll just quickly draw the two mechanisms that we expect for these reactions. For the SN1, we start off with our product, and then the alcohol group from isopropyl alcohol comes in. Then just attacks right there and kicks off the bromine. And then this is how we get our first product. And then for our second, from the elimination reaction, the OH here comes in and deprotonates this hydrogen, forming a double bond, and then kicking off the bromine. And then this is how we get our other product. Okay, so let's see what the junior tutor said. Starting compound is an alkyl halide. Because halides are good leaving groups, either substitution or elimination could occur. We need to inspect the entire reaction carefully. First, we must look at the substrate. Substrate has a 2-degree alpha carbon. This means that it is fairly restricted. Next, we looked at the nucleophile. Our nucleophile here is water, which has no charge. This means that it will not undergo SN2 since this requires a strong nucleophile. Moreover, since water is weakly basic, it is not likely that E2 would occur, leaving only SN1 and E1. That means that either an SN1 or E1 reaction would occur. Okay, so they have the same products drawn out. Generally, E1 reactions are more likely to occur upon heating compared to SN1. Therefore, the major product would be the SN1. Moreover, of the SN1, a hydride shift would occur since a 3-degree carbocation is more stable than a 2-degree, which is why the major product has a 3-degree alcohol. Yep, so this solution is correct. Okay, so question 3 just asks, what is the heat of formation of water? So this can also be described as like enthalpy. So the heat of formation is the change of enthalpy. During the formation of 1 mole of the substance. And this is when it's formed from its constituent elements. So for example, you can have hydrogen gas plus half of an oxygen makes H2O. So there are 2 delta H formation for water. So the first one is negative 241.8 kilojoules per mole. And this is for H2O gas. The second one is negative 285.8 kilojoules per mole. And this is for liquid water. Okay, so the junior tutor said, the standard enthalpy of formation or standard heat of formation of a compound is the change of enthalpy during the formation of 1 mole of the substance from its constituent elements, with all substances in their standard states. Heat of formation of water is negative 241.8, and then they just wrote out the formation reaction as well. Yep, so this solution is correct. I'm also just going to add the value for liquid water. Okay, so on to question 4. Calculate the molar solubility of aluminum 3-hydroxide. Okay, so they also give us the KSP value as well. So let's just define molar solubility. This is the number of moles of solute that can be dissolved per liter of solution before it precipitates. And becomes saturated. Okay, so the first step of calculating molar solubility is just to write your reaction down. So for aluminum 3-hydroxide, this can be broken into its ions. Aluminum 3 plus 3-hydroxide ions. Okay, so everything is balanced. So next we want to construct an ice table. So aluminum this is a solid. So we can just cross out its column. And for our products, they both start off with an initial concentration of 0. C is the change. So the X is the molar solubility, which is what we are trying to solve. And then E is actually 3X. So there are 3 moles. Okay, so we ended up getting X and 3X. And then the next step is to write out our KSP expression. So KSP is equal to the concentration of aluminum 3 plus times the concentration of OH minus to the power of 3. And the KSP was given in the question. It is 2 times 10 to the negative 32. And if we subbed in our X values as the concentrations, we end up getting the following. Okay, so now we just need to solve for X. Okay, so this can be simplified to 27 times x to the power of 4. And then x is equal to 2 times 10 to the negative 32 divided by 27. All of this to the power of 1 over 4. So it's like taking the fourth root. I don't know what that term is called, but and then if you plug it all into your calculator or an Excel sheet, for example, you get a molar solubility of 5.22 times 10 to the negative 9. Okay, so let's see what our junior tutor said. They wrote out the reaction, constructed the ice chart, and found molar solubility. KSP is equal to the concentration of aluminum 3 plus times the concentration of OH minus to the power of 3. They subbed in what they got from their ice table and got the 27 times x to the power of 4. Okay, so I believe the number in the bracket is right, but I think they might have just did a calculation error for the very last step. I'm just going to say that the explanation is correct. Value of x should be equal to 5.22 times 10 to the power of negative 9. Okay, so everything else, all the steps were correct though. I'll just say it is incorrect. Okay, so question 5. What are the products obtained after ozonolysis of the following compounds? 2,4,4-trimethylpent-2-ene, 2-methyl-but-1-ene, and 1-methyl-cyclohexene. Okay, so I'll just write down the definition of ozonolysis and what kind of reaction it is. But just to put it in like easier terms, ozonolysis is when you cleave the double bond or triple bond and converts it to carbonyl groups or C double bonded with oxygen. So it sounds complicated at first, but once you kind of get the hang of how to do the reaction, it gets pretty easy. So let's do the first compound, 2,4,4 trimethylpentene. Pent2ene. If we were to draw it out, our base, our parent carbon chain is 5 carbons long. Oh wait. 1, 2, 3, 4. Oh, I was right. 5. And then I'm just going to number it so that make it easier. And then on carbon 2, there's a double bond. And then also on carbon 2, there is a methyl group. And carbon 4 contains 2 more methyl groups. So our compound looks like this. And then when I draw out ozonolysis reactions, I like to show where the double bond is cleaved. So this will help me when I write out my final products. So when you have an ozonolysis reaction, the reagents are O3 and just any reducing agent. So I'm going to use dimethyl sulfide. And our two reactants, our two products that are formed are just propanone oops. So there's 1, 2, 3, 4, 5, 2, 3, 4, 5. Okay, so the name of this is 2,2-dimethyl propanal. Okay, so notice where I cleaved the double bond. This is where the newly formed carbonyl groups are placed. Let's do the same thing for the next compound. 2-methyl-bute-1-ene. So I'm going to draw my parent chain, which is 4 carbons long. And then there is a double bond on carbon 1. And on carbon 2, there is a methyl group. Again, I'm just going to show where my double bond will be cleaved. And then write down my reagents. And our first product is just formaldehyde. So the simplest aldehyde you could get. And then our second product looks like that. So this is butanone. And then for our last compound, it is 1-methyl-cyclohexene. Okay, so cyclohexene, that means it is a 6-membered ring that has a double bond. And there's also a methyl group on carbon 1. So again, I'm going to draw where the bond will break. And show my reagents. Okay, so let me count out. We should have 7 carbons here. So there's 1, 2, 3, 4, 5, 6, 7. Yep. So if I were to show the same 7 carbons, it would look like that. So this is how this double bond broke. And the name of this is just 6-oxoheptane. Okay, so those are all the products after ozonolysis. Okay, so the junior tutor said, ozonolysis of the given organic compounds follows the general reaction below. So it shows that the double bond breaks and there is now an oxygen in its place. Okay, so their first products, they got 2,2-dimethylpropanal. Yep, and propanone. Yep. For part B, they got butanone and methanal. So methanal is the same thing as formaldehyde. So this answer is correct as well. And then lastly, they showed the structure and got 6-oxoheptanal. So this solution is correct. Moving on to question 6. Calculate the molar mass of naphthalene, the organic compound, in mothballs. If a solution prepared by dissolving 5 grams of naphthalene in exactly 100 grams of benzene has a freezing point 2 degrees below that of pure benzene. Okay, so first I'm just going to write the equation for the freezing point depression of a solid. Or of a solution, sorry. Okay, so this is delta TF is equal to KF times M. So delta TF is the temperature difference between the freezing point of the pure solvent and the solution. KF is the molar freezing point depression constant. And then M, lowercase m, is the molality concentration of the solute. Okay, so for step 1, I'm going to find the molality of the solute just by rearranging that first equation. Since the temperature difference was given, and I can look up the Kf value. So okay, so the Kf value of pure benzene is 5.12 degrees C over M. And the question said that the temperature difference was 2 degrees. Okay, so if we divide this, we end up getting 0.391 M. So the units would be moles per kilogram. So these are the units for molality. Okay, so step 2 is to find the number of moles of solute. And to do that, it is just molality is equal to N solute over the kilograms of solution. Okay, so let's rearrange this. Is equal to 0.391 moles per kilogram. So this was our molality that we found. And then the kilograms of our solute is the 100 grams of benzene. So I'm also going to convert 100 grams to kilograms. And to do this, you just divide it by 1,000. So this is the conversion factor. And then we end up getting number of moles equal to 0.0391. And then the last step is to find the molar mass. And to do this, it's just number of moles is equal to M over capital M. So the mass of naphthalene is 5 grams. And the number of moles we got was 0.0391. So then we get a molar mass value equal to 128 grams per mole. Okay, so if we double checked our answer, I'll draw out the structure of naphthalene over here where I have some space. But basically it looks like this, where you kind of have two 6-membered rings like fused together. And its structure is C10H8. So if we were to find the molar mass of naphthalene, it would be equal to 10 times the molar mass of carbon plus 8 times the molar mass of hydrogen. So if we were to look it up on the periodic table, the molar mass of carbon is 12.01 and the molar mass of hydrogen is 1.01. So if we were to add those values up, you end up getting 128.18, which is pretty much the same thing as our answer. So we know that we got it right. Let's see what the junior tutor said. To answer this, we use the freezing point depression given to us. Recall that we can calculate the freezing point depression of a solution using equation 1. Delta TF is the freezing point depression, which is the total temperature difference between the freezing point of the pure solvent and the solution. AF is the molar freezing point depression constant. For benzene, it's 5.12 degrees Celsius over M. And M is the molar concentration of the solute. So to get the molar mass of naphthalene, we solve for the molar concentration of the solute. Calculation is shown below. So then they also did 2 degrees divided by 5.12 degrees over M and got 0.39. Then we use the molar concentration to get the moles of the solute. Recall that they mean molality is the moles of solute per kilogram of solvent. Okay, so they also got 0.039 moles. Lastly, we divide the grams of naphthalene used by the moles of naphthalene in the solution. So the molar mass of naphthalene is 128. Yep, so this solution is correct. Okay, so moving on to question number 7. Just asks, what is a mole percent? So mole percent, I'll write out the definition. This is the mole fraction of the corresponding element or compound in the overall composition of the mixture. Okay, so this makes more sense when we just do like an example. So for example, let's say we had a mixture that contains 0.17 moles of NaCl plus 5.55 moles of H2O. And then we want to know what is the mole percent of sodium chloride. Okay, so we denote mole percent as just X. So the X of NaCl is equal to the number of moles of NaCl divided by the total number of moles. So the total moles is just the sum of the moles of NaCl and water. Okay, so if we just sub in our values for moles, it's 0.171 divided by 0.171 plus 5.55. Oh, and this whole thing should be multiplied by 100. Forgot to add that part. So that gives us the mole percent. and you should get around 2.99%. Okay, so let's see what the junior tutor said. The mole percent of an element or compound in a mixture is the mole fraction of the corresponding element/compound on the overall composition of the mixture multiplied by 100. This uses the concept of mole fraction, wherein the mole fraction of a substance X on a mixture comprising of X, Y, and Z substances can be computed as. Okay, so the mole percent of X is equal to the moles of X plus divided by the moles of X plus the moles of Y plus the moles of Z. Upon getting the information about the mole fraction of the substance, the mole percent is computed as, so percent moles is equal to X times 100. So this solution is correct. And I think we have time for one more question, which just asks, what is the structure of caffeine? So caffeine is two-membered rings. Well, multi-membered rings that are fused together. So here's a six-membered one first. Okay. So this is the following structure for caffeine. And the junior tutor said, caffeine is an organic compound mostly found in coffee and tea, and has a chemical formula C8H10N4O2. Figure shows the structure of a caffeine. Yep, double bonded carbons. So it's pretty much the same, just a bit different order than mine. This solution is correct. Okay, so that's all the questions that we have for today. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you wanted to submit a question of your own, then check out the links in the description. And don't forget to leave a like and a comment if you enjoyed today's video. And also, don't forget to share it with all your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.